Hello, welcome to this video. I am Karnesh Chauri and today we'll look at socket programming in C language. We'll start with basic socket concepts and build client-server programs using TCP and UDP sockets. Finally, we'll look at the select call and see how the select call can help a server monitor multiple sockets. So, what is a socket? As an example, let's look at this electric socket. Now this is pure hardware and is used by people. It gives a fixed voltage and has a maximum current rating, which means there is a maximum current that I can draw from it. These are fixed and there is no way to change it unless you change the hardware. One needs a matching plug to use the socket, but it is convenient. It gives a nice interface to a complicated electrical power supply system behind it. Now we come to network sockets. Network sockets are conceptually similar but really very different from electric sockets. Just like an electric socket provides an endpoint for electric supply network, a network socket is an endpoint of a computer network, and this is where the similarity ends. Whereas electric sockets are pure hardware, network sockets are pure software. Electric sockets are used by humans, network sockets are used by processes for communication. There are two major types of network sockets: the TCP sockets, which provide connection-oriented communication as per the transmission control protocol, and the UDP sockets, which provide connectionless communication as per the user datagram protocol. A process uses sockets just like it uses file descriptors for input and output. Since network communication is complex, there are specialized calls for communicating over sockets. Sockets are created and configured by processes to communicate with other processes on other computers, which may be in different buildings or different cities or even in different continents. The only requirement is that they must be connected to the internet and be willing to communicate. An Internet Protocol address or IP address identifies a host computer on the internet. Now that is not entirely correct, as a host may have multiple IP addresses. It is more accurate to say that an IP address identifies the network connection on a host. A host may have an IP address for each network interface card and also for the Wi-Fi connection. There are two types of IP addresses, IPv4 and IPv6. IPv4 is Internet Protocol version 4, which was deployed in ARPANET in 1983. We are all very familiar with IPv4. An IPv4 address is 32 bits long and is expressed as 4 unsigned integers, displaying the contents of 4 bytes of address separated by dots. For example, 198.51.100.2 is an IPv4 address. As the internet became popular in the 1990s and more computers got connected, the scarcity of IP addresses for new connections loomed large. So work was started on a bigger address space in mid-1990s. In December 1998, IPv6 became a draft standard and was ratified as an internet standard on July 14, 2017. An IPv6 address has 8 groups which are written separated by colons. Each group has 4 hexadecimal digits. As each hexadecimal digit is 4 bits long, each group is 2 bytes long, and an IPv6 address is 16 bytes or 128 bits long. To simplify writing of IPv6 address, the leading zeros in groups are omitted. If one or more consecutive groups are zeros, these are replaced by double colon. There can only be a single double colon in IPv6 address. As of now, both IPv4 and IPv6 addresses are in use. So the software we develop must work seamlessly with both addressing schemes. The underlying concept in networking is process-to-process communication. Normally, one of these processes is a client and the other one is server. The most common server is the web server. Each website is powered by a web server. Apart from web server, there are other servers like mail server, time server, IMAP server, secure shell server, etc. that may be running on a host. So when a client wants to communicate with a server running on a host, it needs to specify 2 things. First, the IP address of the server host, and second, the server it wants to communicate with. It is here that the port number comes handy. The client uses the port number to identify the server it wishes to communicate with. A port number is a 16-bit integer. Port numbers for certain services are prefixed. You can find all the reserved port numbers and corresponding services in the /etc/services file. We can see that port number 22 is for secure shell server, port 25 is for SMTP server, port 53 is for the DNS server, port 80 is for HTTP, 443 is for HTTPS, port 587 is for mail submission, and port 993 is for IMAP over SSL. Now we look at the socket API, the function, and the system calls. The first is the get ADDR info function. Get ADDR info function translates a host name and a service into a list of socket addresses pointed by res, which can be used in subsequent bind and connect calls. The get ADDR info function gives a linked list of ADDR info structures. Now a struct addInfo contains a pointer to struct sock ADDR, the socket address, and AI ADDR length, the length of the socket address. These two can be used as parameters in bind and connect calls. How does get ADDR info work? The first parameter in get ADDR info is node. It can be an IP address or a network host name, in which case DNS lookups are done and the name is resolved into an IP address. The second parameter is service. It can be a port number, or you can specify a service name like HTTP, and it is translated into a port number. The third parameter is hints, which provide the criteria for selection of socket addresses. Hints can be null or a pointer to a struct ADDR info. In hints, you specify one or more parameters, the address family, socket type, protocol, and flags. If the first parameter to get ADDR info node is null and the AI flags have AI passive set, the socket addresses returned by get ADDR info would be suitable for binding to a socket which would receive connections from clients. In hints, you can specify AI family as AF-INET for IPv4, AF-INET6 for IPv6, or AF-UNSPEC, in which case the system can return socket addresses for any family which can be used with a specified node and service. In AI sock type, the socket can be sock stream or sock DRAM. If 0 is specified in AI sock type, it means socket addresses of any type can be returned by get ADDR info. AI protocol specifies the protocol for the returned socket addresses. A 0 in this field means that socket addresses with any protocol can be returned by the get ADDR info function. In the last parameter res, get ADDR info returns a pointer to a linked list of ADDR info structures. The calling process can scan through this list and select an address. The second function, free ADDR info, frees the memory occupied by the linked list pointed by res. And the third function, GAISTR error, is an error reporting function which translates an error code returned by a function like get ADDR info into a human readable string. The socket system call creates a socket for the calling process. A socket is a communication endpoint. The first parameter is the domain, which can be IF-INET for IPv4 and IF-INET6 for IPv6 protocol family. The second parameter, socket type, can be sock stream for stream sockets, providing a reliable, sequenced, full duplex connection based stream, or socket DGRAM for connectionless, unreliable, efficient delivery of datagrams. The third parameter, protocol, specifies the protocol to be used. Normally, there is only one protocol for a given socket type, in which case it can be specified as 0. The socket call returns the file descriptor for the created socket. The get sock option and set sock option calls are for manipulating the options related to sockets. To work at the socket API level, the second parameter level is solve socket. The next three parameters are for option name, option value, and the length of the option value. When a socket is created with a socket system call, it has an address family like AF-INET, socket type like SOCStream, but it does not have a network address associated with it. With a bind system call, we can associate an address with the socket. The first parameter is the socket file descriptor. The next two parameters are address and address length respectively, which have been obtained earlier using the getAddr_info function. Listen marks a socket as a passive socket. This means that the socket will accept incoming connections using the accept call. SOCFD is the file descriptor of the socket and backlogs the maximum number of connection requests that can be pending in the queue at any time. The accept system call is used for connection-based sockets. The first parameter, SOCFD, is a socket created with the socket system call with a network address associated with the bind the call and is listening for connections after the listen call. Accept takes in the first connection request in the queue, creates a new connected socket for communication with that client, and returns the file descriptor for the newly created socket. The original listening socket is not affected. Accept also returns the socket address of the client in buffer pointed by the second parameter ADDR, and the length of the socket address is returned in location pointed by the third parameter ADDRLen. If there are no connection requests and the socket is not non-blocking, accept blocks till a connection request comes in. However, if the socket is marked non-blocking and there are no connection requests, accept returns -1 and the error number ERRNO is set to E again or E would block. It is important to note that the buffer for storing client socket address has to be provided in the accept call. Just how long should this buffer be? Our server should cater to both IPv4 and IPv6 protocol families, and the buffer provided should be large enough for that. Let's take a quick look at the socket address structures in the header files. Now this is the socaddr.h file, and it says SS size is 128 bytes long. This is the size of struct socaddr storage and is large enough to hold both IPv4 and IPv6 socket addresses. We can see that struct in ADDR is for IPv4 address and struct in6_ADDR is for IPv6 address. The struct for IPv4 socket addresses is struct socaddr_in, and the struct for IPv6 socket addresses is struct socaddr_in6. So in the accept call, instead of passing a pointer to buffer of size struct socaddr, we pass a pointer to the buffer of size struct socaddr storage after typecasting it to pointer of struct socaddr. After the call returns, we check SS family, the first member of the struct socaddr storage. If SS family is AF-INET, we typecast the structure pointer to struct socaddr_in pointer. Otherwise, if SS family is AF-INET6, the structure pointer is typecast to struct socaddr_in6 pointer. The connect system call is used by a client to connect to a server. The connect call connects a socket identified by SOCFD to the address specified by the second parameter, ADDR pointer. The third parameter, ADDRLen, gives the length of the socket address pointed by ADDR. The send system call is used to transmit a message on a connected socket, identified by the first parameter, SOCFD. The second parameter, buff, points to the message, and the third parameter, len, is the length of the message. The last parameter is for flags. The RECV call is for receiving messages from a connected socket identified by the first parameter, SOCFD. The second parameter, buff, points to the buffer for receiving data, and the third parameter, len, is the length of the buffer. The last parameter is flags. RECV returns the length of the message actually received. Computers can be classified into two types based on the internal representation of numbers. The first is the little endian machines, in which the address of a number is the address of the lowest order byte. And the second are big endian machine, in which address of a number is the address of the highest order byte. The Intel x86 and AMD 64 based computers are little Indian machines, and Motorola 68K based machines are big Indian. So if a number is sent between different Indian machines, it would appear to be scrambled. To prevent this, a network byte order is defined, which is big Indian. All numbers should be sent on network in the network byte order. There are utility functions to convert from the host byte order to network byte order and vice versa. H2NL and H2NS convert 32 and 16-bit unsigned integers respectively from the host to network byte order. Similarly, N2HL and N2HS convert 32 and 16-bit unsigned integers respectively from the network to host byte order. Now we have an example quotation server program using stream sockets. The server runs on public IP address and accepts connections over a publicized port. Clients connect to the server and ask for quotations. This is the source code of the server. The port is 4356. Struct client info. This is the information about the client. It stores accepted socket ID and also the client socket address. And we have an array of clients whose each element is a struct client info. This is the structure of a message. It has two parts, message ID and a buffer. The server starts. It does a get ADDR info. It passes null for the node. And the port is quote server port, which is 4356. Then hints. The AI family is AF unspec, which means we are okay with either IPv4 or IPv6. AI socket type, our socket should be stream socket, and AI flags is AI passive. Now, since the node is null and the AI flags is AI passive, this socket would be able to accept connections from clients. We get the results from get ADDR info and we scan the results for a suitable socket. For each result, using the return value of AI family, AI socket type in AI protocol, we try to create a socket. If socket is okay, then we set socket option SO reuse ADDR so that when we run our program in quick succession, we don't get address already in use error from the bind call. Next, we tried the bind call with the socket FT and the socket address values returned by get ADDR info. If successful, we break. Otherwise, we go to the next iteration. Once we are through with bind, we free the result linked list and do a listen call for the socket and thus mark it for accepting incoming connections. Now we have the loop. The loop is about accepting new connections for a client and starting a thread for new client. First, we get a slot for the new client in the client's array. Then we wait for a connection from a client. When the connection request comes, we accept it. The new socket ID is stored in the accepted socket ID and we start a thread to execute handle client function for the new client. In the handle client function, we print the IP address of this new client. Then we start the loop for this client. An iteration in this loop is simply receive a message from client using RECV call, look at the message ID to decipher what client is asking for. The client can ask for only two things, a quotation, in which case select a random quotation and send it to the client using the send call. Or the client says I quit. In that case, the server cleans up the entry for the client in the client's array. The loop is over and so is the handle client function and the thread for the client. So this is how the server works. Now let's look at the client code. The client is invoked with the command client hostname. The first parameter gives the hostname of the server. The server port is hard-coded and the client does a get ADDR info to get the socket address of the server for the connect call. The client scans the result linked list. For data in each element of the linked list, the client tries a socket call and if that is successful, it tries to connect with the server. Once that is successful, the loop terminates. Now we have the main loop of the client. The client gets input from the user and either asks for a quotation or quits. If the client had asked for a quotation, it gets from the server. It prints the quotation on the screen. We can compile the server and client programs. GCC code server.c -o code server -lp thread, GCC client.c -o client, and we run the server. Also, we can run multiple client programs and get quotations. With this, we complete the first part of the video regarding stream sockets using the TCP. We'll next look at the datagram sockets using UDP. Datagram sockets provide connectionless communication as per the user datagram protocol UDP. UDP is unreliable and messages may get lost in transit. Messages are not ordered and may arrive out of sequence at the destination. However, there is a checksum in the packet, and if a message arrives, its integrity is guaranteed. UDP is a small transport layer on top of Internet Protocol IP, so it is very fast and is suitable for real-time systems, games, voice over IP, video and audio streaming services, broadcast and multicast, etc. Loss of some packet causes slight degradation of service. However, the application does not fail and continues to provide fast, near real-time response. Send to is the call for sending a message to a remote datagram socket. SockFT is the file descriptor of the local socket. Buff points to the message and len is the length of the message. The fourth argument is flags, which can be 0 in most common cases. Dest ADDR points to the destination socket address and ADDR length is the length of the destination socket address. If send to is successful, it returns the number of bytes actually sent, and if it fails, it returns -1 and ERRNO is set accordingly. RECV from is a system call for receiving messages on a socket identified by the first parameter SockFT socket file descriptor. Buff points to the buffer where received message is stored and has to be provided by the caller. Len is the length of the buffer. The last two parameters, sock ADDR and ADDR len, the address of the remote socket and the length of the remote socket are returned. And again, the buffers have to be provided by the caller. The fourth parameter is flags. RECV from returns the number of bytes actually received on success. If it fails, it returns -1 and ERNO is set accordingly. If there are no messages, RECV from blocks till a message comes. Now if you don't like this default behavior, you can specify MSG don't wait as flags, in which case, if there are no messages, RECV from returns -1 with ERNO set to E again or E would block. And we have an example, server and client that communicate over datagram sockets using the UDP. Our server is the temperature server. It keeps a record of last reported temperature of a city. Clients report temperature of cities to the server and also inquire about temperature of a particular city. Here is the server code. The server port is 4357. The clients send one of the messages, store temperature, in which case the client is asking server to store temperature of a city, and 2, read temperature, in which case the client is asking the server for the temperature last recorded for a city. And this is a message structure. It has message ID, which is one of the 5, stored temperature, read temperature, etc. Then the name of the city followed by temperature in Celsius in character format. The server stores temperature in a binary tree so that when asked for a temperature of a city, it can find it fast. There are 2 message structure, one for receive message and one to send message. And there's a function to add a temperature record to the binary tree and also to find the temperature record for a city in the binary tree. The server starts, it does a get ADDR info for itself, then it creates a socket, assigns an address to it using bind. Once this is done, we have the infinite loop. The server waits for a message from the client. Once the message comes, it can be either store temperature message or a read temperature message. In both cases, server validates the input value for the city name and temperature. Once validation is through, for a store temperature, it adds or updates the temperature record in the binary tree. In case of read temperature, it finds the record and sends the result to the client. This is how the server works. Now let's look at the client. The client does initialization, creates a socket for communication, and client creates 2 threads, one to receive messages from the server and second to send messages to the server. So there is a dedicated thread to receive messages. Now let's look at the client send thread. It gets input from the operator, whether operator wants to store temperature or read temperature and makes a message and sends it to the server. Note, it does not wait for a reply. This is unreliable communication, and either of the messages from client to server or server's reply might get lost. So receiving messages is delegated to a separate dedicated thread, and the client receive thread receives messages on the SOC FD and prints the message from the server for the operator. This is how the client works. We can compile the server and client programs. gcc server.c -o server, gcc client.c -o client -lp thread, and we run the server and multiple clients. We have completed the second part of this video, which is regarding Datagram sockets. Next, we'll look at the select system call in the third and final part of this video. Let's revisit the first example about stream sockets. Here, the server waits for connections from clients. After the server accepts a connection from a client, it creates a thread, handle client, for further communication with the client. So for each client that connects with it, the server creates a new thread. This may be okay for a few clients, but certainly as the number of clients increase, there will be a 1:1 increase in the number of threads and server performance will degrade. So we do away with the one thread per client algorithm and look for a way to find which file descriptors have data ready for reading and go ahead and read from those file descriptors. The select system call helps us to do that. The select call sets up monitoring of three sets of file descriptors. The three sets are specified by set pointers passed to select call as arguments 2, 3 and 4 respectively. The file descriptors in the set pointed by read FDs are monitored whether any of these are ready for reading. A read on a ready file descriptor would not block. The file descriptors in set pointed by write FDs are monitored whether there is space for a write operation, and the write operation on a file descriptor would not block. However, a big write might still block. The file descriptors pointed by except FDs are monitored whether any of these are having an exception condition. The first parameter to select n FDs is the largest file descriptor in the sets plus 1. The last parameter is a timeout is specified as a pointer to struct time well. If none of the file descriptors is ready and a timeout occurs, select returns. If timeout is null, select would wait until at least one file descriptor is ready. The pointers to one or more sets could be null and these sets are ignored. When select returns, the file descriptor that are ready are set in the respective sets. So select modifies the sets and the sets have to be reinitialized before the next select call. Select returns the number of file descriptors set or -1 on error. There are 4 macros for updating file descriptor sets. FD0 initializes a file descriptor set, clearing all file descriptors in it. FDset sets a file descriptor in the set. FDclear clears a file descriptor in the set. FDIsSet is for checking whether a file descriptor is set in the given file descriptor set. Select call can only monitor number of file descriptors less than FD set size, which is hard-coded as 1024. And we have an example. Flight time record and query system. The server keeps a record of flight arrival and departure times at an airport. Clients can request to server to store flight times, and clients can also query the flight times. This is the server code. The server port number is 4358 and this is the message structure. There is a 32-bit message ID followed by flight number, arrival departure flag and date and time. The server keeps flight data in a binary tree. Each node has a flight number, arrival departure flag, flight time, left and right pointers, and you have structures for receive message and send message. The server starts, does a get ADDR info for itself. Using the results of get ADDR info, it creates a socket and binds an address to it. It marks the socket for accepting incoming connections with a listen call. It creates two sets of file descriptors, FDs and read FDs. Initial value of FD max is listener socket FD and FDs is initialized with listener as that is the only FD at this point. We get into the while loop. Read FDs is set to FDs, the set of all file descriptors. We make the select call with read FDs. The fact that select call has returned means that some sockets are ready. We examine all sockets from 0 to FD max. For each socket, if socket is the listener, then it is a request for a new connection. We do an accept and get a new file descriptor. We set this new file descriptor in our FDs, and if this is greater than FD max, we set FD max to this new file descriptor. And if FD is not listener, it is a request from an existing client. Request can be store flight. We validate data, and if it passes validation, we store the flight record in server database. Request can also be query of flight time. We find the flight record, and if there is a flight record, we send data to the client. And there are functions to add to the binary tree and read a flight record from the binary tree. This is how the server works. And this is the client code. The client obviously has the same message structure as the server. The client starts. The usage is client hostname of the server. Client does get ADDR info. It opens a socket and tries to connect with the server. If the connect is successful, it gets to the while loop. Client takes input from the operator. Operator can choose flight time query or store flight time. Based on operator's choice, it builds the message to be sent to the server. If it is flight time query, it asks for flight number and message is sent to the server. If it is to store flight time, it asks for flight number, arrival or departure, flight date and time, and the message is sent to the server. Then it waits for the server to respond. When the server's response comes, it prints the results for the operator. This is how the client works. We can compile the server and client programs. GCC flight time server.c -o flight time server. GCC flight time client.c -o flight time client. We run the server and we run the client from multiple windows. You can find all this information at http://bit.ly/stream-sockets and http://bit.ly/datagram-sockets and http://bit.ly/select-syscall. With this, we come to the end of this video. Thanks very much for watching. Have a good day.